Hello, I'm Oliver. Thank you for listening to my presentation. Every year, the world produces around 6 million tons of cathode ray tube waste. Because all these tubes contain lead, mercury, and cadmium, they're classified as hazardous waste. Yet, many still contain high-precision, usable electron guns. My process aims to prove that you can feasibly control these old technologies using modern microcontrollers and cheap, accessible off-the-shelf components. In doing so, I hope to prove it's possible to repurpose some of these old tubes for uses in education. Firstly, a cathode ray tube consists of a few parts. Here's the ones that are most important to mention. You have the cathode, which is heated up to emit electrons via thermionic emission. You have the anode, which is a very high positive voltage relative to the cathode. You have the focus anode, which focuses the beam, and you have the deflection plates, which moves the beam. To generate the high voltage swings needed for the deflection plates, I started by using a Raspberry Pi 5 and a 12-bit DAC to generate a precise 0 to 3.3 volt control signal. But the beam needs to be around 350 volts in order to actually move, so I had to amplify it, so I designed a custom 4-channel linear inverting amplifier. This circuit effectively just takes a small input voltage of around 0 to 3 volts and increases it up to 0 to 350 volts, ideally keeping the ratio the same but flipping it around. This amplifier had its own separate power supply because it drew too much current to be powered from the same power supply as the tube itself. This is foreshadowing. Because this is so high voltage, I didn't want to fry my low voltage Raspberry Pi again, so safety was critical. So I 3D printed a modular rack to physically isolate the high voltage components with plastic and air to make sure no wires could touch by accident or arc. To drive the display, I wrote a custom vector rendering engine, which uses linear interpolation to calculate the intermediate points between vertices, ensuring the beam moves at a constant speed to maintain uniform brightness. Before touching the hardware, I validated my logic using a Python-based simulation to ensure my coordinate mapping was accurate without risking the delicate hardware. In engineering, though, things never really go how you want them to go, and even more so with high voltage. Last minute, I somehow managed to fry my power supply for the amplifier, so I was forced to use the same power supply for the tube and the amplifier, which resulted in a much dimmer image than intended, and I couldn't power all 4 amplifiers at the same time, so I couldn't test the proper vector rendering engine. However, I did show that the amplifiers do work by testing just one of them on simple signals, such as a square wave and a sine wave, and I did show that it works with those signals, so I do think, even with all my errors considered, I do think I proved that modern digital logic can successfully control decades-old vacuum tube technology. My next steps will be to replace the dedicated power supply to achieve full brightness, and I'm going to perform precise measurements on the beam's linearity. Thank you so much for listening to my presentation.